Do you really need to know math in order to work with deep learning? An argument goes that no, you just need to know high-level libraries like PyTorch or TensorFlow. But in reality, if you really want to understand how neural nets work, then yes, you need to know a bit of linear algebra. So that's why in this video, we're going to talk about vector and matrix operations. So let's get started with vectors. What are vectors? Well, vectors are just arrays of numbers. We notate vectors with small caps, bold letters, like this A vector here, and then we can arrange a vector that's a collection of different items, both horizontally, and then we have a row vector, or vertically, and we have a column vector. So on vectors, we can perform a number of different operations. Some that come to mind, and that are the simplest ones, are scalar operations. These operations involve a vector and a scalar, which is basically a number, like 2 or 3.5, for example. And we have scalar additions, subtraction, multiplication, and division. So let's take a look at scalar addition, for example, and the argument goes with all of the other scalar operations as well. So here we have the vector A, and we add the scalar n. And so as you can see here, the result is this vector here, and the vector is given by the A1, which is the first element of the vector, plus n, which is the scalar, and then A2 plus n, A3 plus n. So basically, we add the scalar to all the items of the vector. So let's take an example here. So we have a vector, this column vector, which is 1 to 2, and we want to add 1. And the resulting vector is 2, 3, 3. We just added 1 to 1 here, 1 to 2 here, and 1 to 2 here. It's very simple, isn't it? Then we have other types of operations, like vector addition and subtraction. So here, the operations are performed between two vectors, and that's a constraint here. So the two vectors must have the same dimension. So, and what's a vector dimension? Well, it's very simple. It's the number of items that we have in a vector. So in this way, for example, here, we are adding up the vector A plus the vector B, and as you can see, both vectors have the same number of items. So 3 items for the A vector and 3 items for the B vector. So vector addition and subtraction are element-wise operations, as you can see here. So what this basically means is that we add the first element of the first vector to the first element of the second vector, and this is going to be the first element of the sum vector in this case. Then we do the same thing with the second items. So A2 plus B2 gives us the second element of these of the sum vector, and finally here A3 plus B3 is the third element of the sum vector over here. So again, let's take a look at an example, just like to see this more clearly. So here we have two vectors, so 1, 2, 3, and 3, 5, 6. So we want to add them up together, and so the sum vector over here is 4, 7, 9. So 1 plus 3, 2 plus 5, that gives us 7, and 3 plus 6, that gives us 9. So this is very simple, isn't it? Now we have another operation which is super important, as we'll see in a second, for neural networks as well, and it's called the dot product. Again, the dot product is performed between two vectors, and the result this time is a scalar, so it's a number, so it's not another vector. So how do we notate a dot product? Well, and not surprisingly, we noted dot product with a dot. And as you can see here, so we have the dot product that's given by, so that we can perform between two vectors over here, and the result of the dot vector over here is A1 multiplied by b1 plus a2 multiplied by b2 plus a3 multiplied by b3. So how do we get to this formula over here? Well, it's quite simple. So we take the first item of the first vector and we multiply that with the first item of the second vector, and then we add to this the second item of the first vector multiplied by the second item of the second vector, and so on and so forth. So now let's take a look at an example here. So we want to perform the dot product between two vectors, so 1, 2, 3, and 4, minus 2, 1. So the result here is 1 by 4, and we've reached this by multiplying the first element of the first vector with the first element of the second vector. So 1 by 4 plus 2 by minus 2. So multiplying the second items from the first and the second vector plus 3 by 1. And we achieve this by multiplying the third item from the first vector by the third item from the second vector. So now if we run the math here, we come up with a number that's 3. So the dot product in this case is 3. Nice. So I just said before that the dot product is super important for neural nets. So let's revisit something that we've seen in the previous video. So if you remember, so this is an artificial neuron. These x1, x2, x3 are the inputs, w1, w2, w3 are the weights, and here we have the neuron that does two things. So one is the weighted sum, or the net input, and then we have the activation. So let's just focus on the net input now. So if you remember, the net input h is the weighted sum over all the inputs. In other words, is x1, input 1 by weight 1 plus input 2 by weight 2 plus input 3 by weight 3. Now, if you look at these, you may just think that we can rewrite that using the dot product, because it's basically the very same result. And indeed, we can rewrite h as the dot product of x and w, where x is this x1, x2, x3 vector, which is basically it's called the input vector, and it puts together this x1 input, x2 input, and x3 input. And then we have this w1, w2, w3 vector, that's the weights vector. So in other words, we can rewrite the net input as the dot product between the inputs and the weights. And as you can see, obviously the result here, x1 w1 plus x2 w2 plus x3 w3 is equal to the net input as we calculated it last time. So how's this interesting? So why can't we just use this notation? Well, it turns out that this is like way more elegant. So working with vector, and as we'll see with matrices, like it's way more elegant and way faster in terms of notation than just using like all of these like symbols like in an extended form. So this is why we basically use a lot of like dot products and linear algebra for notating neural nets, and that's very, very convenient. So this was it like for the basic operations for vectors. Now let's move on to matrices. So what's a matrix? So a matrix is a rectangular grid of numbers. It's like a spreadsheet, really. So you have a spreadsheet with a lot of like variables or numbers, and you can store all of that information in this kind of like squared rectangular grid. So we notate a matrix using an uppercase letter, so just like here, a uppercase A, and then we have these two weird indexes here, so I and J. So what do they represent? Well, I represents the rows indexes and J represents the column indexes. So let's take a look at these like in actions. So A11 is the first item we have here, and as you can see, this one in this like a red square indicates the fact that we are on row number 1, whereas the second one over here represents the fact that we are on column number 1. So this element here is the element that stays in row 1, column 1. So now let's move on to A12. The 1, again here, represents the fact that we are on row number 1, but the 2 represents the fact that we are on column number 2. Now A21, here we have row number 2, and then 1 indicates that we are on column number 1. So this way we can identify the position of all the elements of a matrix just by using two indexes. I, which stands for rows, and J, which stands for columns. It's as simple as that. So a very important element of a matrix is its dimension. So, and the dimension is indicated by the number of rows and columns. So here we have two matrices here. So like on the left, the dimension of this matrix is 3 by 2. And it's 3 because it has 3 rows, and it's 2 because it has 2 columns. Whereas the matrix on the right is 2 by 3. And 2 is the number of rows we have, and 3 is the number of columns we have. So remember, dimension of a matrix is indicated by number of rows first and then number of columns. So there's a specific case of a matrix which can be used to indicate vectors, and we can indicate vectors as a row. So we can, as we mentioned, we have both like a row vectors and column vectors. And a row vector is indicated by a 1 by n matrix, and a column vector is indicated by an n by 1 matrix. Let's just take a look at an example because it's going to make things like way clearer. So here on the left, we have this row vector. So it's 1, 4, 3. And as we can see here, it's a 1 by 3 matrix. It's 1 because it has only 1 row, and it's 3 in terms of columns because obviously it has 3 columns. And then here on the right, we have a column vector, and this column vector can be thought as a matrix, and it's a 4 by 1 matrix. It's 4 rows here, and it's only 1 column. So this is a nice way of thinking vectors as matrices. An important operation that we have with matrices, it's called transposition. So with transposition, what we do, it's quite simple. So basically is we switch rows and columns. So let's take a look at this matrix, for example. So here we have this matrix which is 1, 2, 3, minus 4, 0.5, 1. And it's a 3 by 2 matrix. Now the transpose matrix, which is indicated with a superscript capital T, which stands for transpose, it's basically the same matrix, but as you can see here, the columns have become rows. So here we had in the first column 1, 3, 0.5, and here the 1, 3, 0.5 has become the first row. So we've basically switched rows and columns. So it's all you have it here. And a simple way of notating this in a very condensed manner is this down here. So the transpose matrix A of ij is basically A of ji. So we've inverted the two indexes for the columns and the rows down here. Okay, so now let's take a look at scalar operations, because we also have scalar operations for matrices. And so here we have addition, subtraction, multiplication, and division of matrices with a number. And they work in a similar manner to scalar operations with vectors. So here, for example, you can see a scalar multiplication. So we have a scalar, which is this n. It could be like any number, so say for example 3, and we want to multiply it by this matrix A, and the result over here, it's quite simple. So we multiply every index, every element in the matrix by n. So the new matrix is, for example here, in the first in the index, like in column of row 1, column 1, is n by a11, then we have n by a12, and so on and so forth. So it's super simple. Same thing with subtraction, addition, and division. We do the very same thing here. So another type of operation is addition and subtraction. So here we have two matrices, and here we also have a constraint. So the two matrices must have the same dimension. So they must have the very same number of rows and columns. And this is an element-wise operation because we, in the case of addition, for example, add up the elements with the same indexes together from the first and the second matrix. So let's clarify this by taking a look at this example down here. So we have this matrix A, B, C, D, and we want to add a second matrix, which is 1, 2, 3, 4. And as you can see here, the sum matrix here is given by the addition of the elements of the first matrix with the respective elements of the second matrix. So for element 1, 1, so row 1, column 1, we are adding A and 1 together. So A being the first being element in row 1, column 1 from the first matrix, and 1 being element 1, 1 from the second matrix. And then we do the same thing for element 2, 1, so row 2, column 1, and here we add B plus 2, and as you can see here, so here we have B and here we have 2, then we do C plus 3 and D plus 4. So it's very simple, and in this way we can calculate super easily both addition and subtraction. So now the problems, I would say, like start to come in when we talk about matrix multiplication. This is a little bit more complicated than all the other operations that we've seen so far. So first of all, there are certain weird constraints on when we can perform matrix multiplication. So we have, again, two different matrices and we want to multiply them. But then, in order to multiply them, we need to have that the number of columns of the first matrix should be equal to the number of rows of the second matrix. Now, let's take a look at this example here. So we have this 3 by 2 matrix and this 2 by 2 matrix here. Now, we can multiply these two matrices together because, as we said, the number of columns of the first matrix, which in this case is 2, and you can see it here, is equal to the number of rows of the second matrix here, which is 2. Now, the result of this multiplication is a new matrix itself where the dimension of this new matrix is given by the rows of the first matrix that we want to multiply and the number of columns of the second matrix that we multiply. So in this case, given in this multiplication, in this example we have here, given we have the first matrix which is 3 by 2 and the second matrix which is 2 by 2, now the product matrix here is going to be 3 by 2. Right, so you may be wondering, how do we get to these results? So let's just like perform this matrix multiplication here step by step. Okay, so as you can see here, the first element here, so the element 1, 1, so row 1, column 1, is given by the dot product of the first row of the first matrix with the first column of the second matrix that we are multiplying. So another way of visualizing this is just by writing it like this. So we have the this vector 1, 2, and we do the dot product with AC, and the result, now we should know it because we know the dot product is 1A plus 2C. So, and this is like what we are performing here, and this result gets logged in position 1, 1 because it comes from row 1 and column 1. So now let's move on with this very simple algorithm to understand how to perform all of the perform multiplication and create the new matrix and all of its elements. So now we can shift the column vector here, and so we have here the dot product between the first row of the first matrix and the second column of the second matrix, and we log these dot products here in the element 1, 2, so row 1, column 2. Now, not surprisingly, you'll see that we'll switch down to the second row here, and we'll do the dot product of this second row with the first column of the second matrix, and this is 3A plus 4C, and we log that in element 2, 1. We'll switch, and we'll have element 2, 2, and then we'll switch again, and then we'll move to the third row, and here we have the third row by the first column with the dot product, and here we log this in element 3, 1, and then the final element will be the third row here, dot product, second column, and here the result is logged in element 3, 2. Cool. Sorry. So we can rewrite a matrix multiplication in a way like that's easier like to remember. So again, if you think of, like, for example, like this 1, 2 as a row vector, and it's row vector A1, because like this is matrix A and this is matrix B, so this is A1, and then we take a look at this second row vector here and we indicate it as A2, and we look at this B matrix here and we call this column the column vector B1 and this second column the column vector B2, then the matrix multiplication over here is given by A1 dot product B1 for element 1, 1, then A1 B2 for element 1, 2, and then the dot product between the A2 row vector and the B1 column vector for element 2, 1, and A2 dot product B2 for element 2, 2. So this is like a very simple way of remembering how a matrix multiplication works. So this was a little bit like weirder than all the other operations that we've seen so far. But as you'll see, this is very, very important because we can use all of this notation to easily capture how a neural network performs its computations. And that's what we're gonna see in the next video. So we're gonna look at neural networks and specifically at multi-layer perceptrons and see how they compute the information when the signal moves from left to right. So this was it for this very quick, I would say like very quick introduction to linear algebra. I hope you enjoyed this, and if you liked the video, please subscribe. If you have any questions, just leave a comment in the comment section below. And if you like the video again, just like it. So I hope I'll see you next time. So bye for now.